Oh, okay. So it's
Got it.
recording now, right?
Yep.
Okay, awesome. All right. Good morning, everyone. Thank you for being here very early in the morning. So today I'm going to we're hosting this webinar with our colleagues, Dr. Stephanie Yong from Cal Poly, Dr. Selena Wang from UC Davis, and Dr. Haibo Huang from Virginia Tech, to talk about a finished project to utilize olive pomace for to enhance their economic values and environmental sustainability. And so this project is funded by USDA through CDFA with the Specialty Crop Block Grant. And Dr. Stephanie Yong at Capoli is serving as the PI, principal investigator for this project. And then Dr. Selena Wang, myself, and Dr. Haibo Huang were the co-PI. So each of us will be talking about one objective for this project. So I'm going to give a quick overview at the very beginning. And if you have any questions, please feel free to type in the chat. And then because of the time limit, we'll address all the questions at the very end. So I will start with a quick background, and then each of us will dive into the details for each objective, and then we'll wrap up with the Q&A session. So since many of you are working in this olive industry, you probably know better than me how olive oil is produced. So when we produce olive oil, almost 70–80% of the biomass goes into the olive pomace, right? And sometimes, if you depending on the process you take, you either separate the olive stone or not. But those olive byproduct end up with animal feed, either with fertilizer or landfill. And right now, although they're being utilized, but they're not optimal because when they're used for cattle feed, it suffers from low protein content and poor digestibility, because we know rumen, they utilize a lot of microbial fermentation in the rumen to digest those foods. So the high phytotoxicity or antimicrobial activity of the olive pomace will inhibit those microbial activity, and then hence it will inhibit the digestion process. And also the fiber content is very high. There's a lot of lignin, cellulose, and xylem in the compound, which will lower its nutrition value. And when used as fertilizer, it's same issue due to the phytotoxicity, because it inhibits the microbial growth. It also inhibits the germination process, and then interfere with the soil microbiota, and kind of break that tiny ecosystem. So those issues will make it not as a good fertilizer. And then for landfill disposal, there's always some regulation challenge, and the greenhouse gas emission issue. And when we want to utilize the olive pomace, the first thing we always want to see is what are inside there. So we actually did a bunch of literature review and trying to see what are the compound there and how can we utilize them. So one thing that we did notice is that there's a very high polyphenol content, like hydroxyl tyrosol. Those are high value compound that if we extract them out, they can be quite economically feasible. And on top of that, we can also utilize those lignocellulosic compounds like lignin, pectin, xylem, cellulose, and those compounds can be either converted to carbon-based material like biochar, or we can convert them into biogas or biofuel. So that comes to our approach here is to utilize every component possibly in this olive pomace, and see which way we can maximize the economic output, and also at the end, we also do a techno-economic analysis, because every step that we add to extract the compound involves the capital investment and operation cost. So we want to see at which compound creates best revenue and with a minimal investment, right? And of course, we can use everything, but sometimes they're not optimal case. So every step we have to see the conversion rate, how well the compound is performing, how much we can sell, and then eventually we will get a payback time for each case scenario. So this is our kind of closed loop circular bioeconomy approach. So the idea is really to minimize the discharge to the environment and then utilize as much as we can. So when we have this olive pomace extracted, with the olive oil extracted, there are usually three waste streams. The first one is the olive meal wastewater, and the second one is the olive pomace, and then sometimes we get olive stone, sometimes we don't, right? So so for this olive pomace is something that we'll be targeting in this project. So for the phenolic compounds in the olive pomace, as I mentioned, which is very high value, we'll extract them out using solvent, and then those can be a commodity for sale at pretty high price. And then the leftover will be soluble carbohydrates and insoluble fiber. And those compounds, if we treat them well, they can be converted to biogas, which is a biomethane, which can be used as a fuel, as an energy. And the leftover, which is not fermentable, we can carbonize them and make into biochar. And in some process, we have the olive stone or olive pit separated out, and then in that case, the olive pit can be fed into the carbonization process as well to make biochar. And the biochar can be circled back to treat the olive meal wastewater, and so that if the water meets the criteria, then we can discharge it or use as agricultural water. And then this biochar with all the nutrients absorbed from the wastewater can then be used as soil amendment to grow this olive. So the idea is to build this closed loop bioeconomy approach. So now I will have each of my colleagues to dive into each objective. So the first part will be Dr. Selena, I think Dr. Selena Wang's extraction of the polyphenol into value-added antioxidants. And I'll turn the floor to Selena.
Good morning. Thank you, everyone, for being here this morning. So our task for this project is fairly straightforward. It's something our lab has been working on for quite some time. Essentially, extract the valuable phenolics from olive pomace, figure out what they are and their concentration, and then provide the olive pomace that has the phenolics taken out to our collaborators. And this work was done in my lab by our former postdoc, Fei Zhao, and a current PhD student, Saint Lowenthal. So I will be presenting some of the findings that we have today. So just as a refresher for those of you who may not know or may not remember all the chemical names of the phenolics in olive oil byproduct. So it's mostly in different classes of compounds, and there are phenolics, phenolic acids, and flavonoids. And these are compounds that tend to have antioxidant, antifungal, antimicrobial properties. Depending on what they are and their potency, they will have different value and different applications. And just kind of to put this on the scale, so we all know extra virgin olive oil is full of antioxidants and phenolics, and there's actually a lot of that's in olive pomace because many of these phenolics are more water soluble, so they tend to go with the water phase doing separation of olive oil production. So if we, let's say an average olive oil, extra virgin olive oil with a phenolic content about 200 milligrams per kilograms of oil, then 1 gram of dry olive pomace would provide the same amount of phenolics as 200 grams of extra virgin olive oil. So just to show some of the material that we work with in our lab. So you have fresh olives that's very high in compounds like oleuropein, which is very bitter. And this is why we cannot eat olives straight off the tree like we can do with apples. And then you have the olive pumice paste that is wet and very unstable in terms of how fast they degrade and then start fermenting. You probably have all smelled the unique uh, aroma of olive pumice paste. And then, but you could dry it to stabilize that. So taking out the moisture, the water activity from olive pumice will help to have this olive pumice last for a long time. But this drying process takes investment, takes energy. But you could also dissolve or the dry olive pumice in various solvents, so you can have a liquid extraction. So instead of a powder form, you could have a liquid form of this. You can then dry that to further stabilize that and then reduce the volume. So then reduce the storage that's needed for this byproduct. So then you end up with the freeze dry powder. Again, this freeze drying process takes time and energy and investment. And then this is kind of the material that we've been working with in our lab. So the solvent that we know that gave us the best extraction for the phenolics is 70% methanol. However, that's not exactly environmental friendly. So a more environmental friendly option is 70% ethanol. But even the more environmentally friendly extraction is just water. So these are some of the liquid extractions that we've been using in our lab when it comes to olive pumice. So not from this project, but I want to show this because it demonstrates the antimicrobial property of olive pumice. And this is just for the water extract. So no solvent that was used when we're dealing with taking the phenolics out of olive pumice, just water. And we were able to find more than 5 log of reduction when it comes to E. coli and Listeria. So this work has been published, and then you really demonstrate the ability of antimicrobial treatment when it comes to olive pumice. And this is something that we didn't see when we were studying other agricultural byproducts. So this is largely due to the individual phenolics, but also the synergetic interactions of different phenolics. Because when we try to do the same study with just one individual phenol, we didn't see the same impact. So it's the combination of phenols together that resulted in this antimicrobial activity that's unique to olive pumice. And this is a visual. We apply the olive pumice to pomegranate arrows, so the parts that you eat out of pomegranate. And on the left is without. This is after 7 days of storage. And on the left, you can see they kind of start losing water weight and turning brown. And on the right side, under the same storage time, the same storage condition, and on the right side with the olive pumice applied, we didn't see the same degradation. Okay, so for this project, again, I mentioned that our task is relatively simple. We start with wet olive pumice. We did a 70% methanol extraction because we wanted to see if we can get all the phenolics out of that. We also did water extraction, and then we measured the phenolic content, and we also use 70% ethanol as well. And here's the data. So we know, so for methanol here, we were able to get relatively good amount. Okay, this is at a small scale, I should say. This is about using like 0.5 grams of olive pumice. This is an analytical scale. We wanted just to see if we're able to see, to get all the phenolics out of olive pumice using our extraction system. So we try methanol, we're able to get a lot of it out. We try water, a little less efficient, but it did show that the water exhausted ethanol fraction had no phenolics left. And then that's the part that we will give to our collaborator. So the next task is we need to scale this up. Oh, sorry, before we get to that, actually, we do have individual phenolics. So this is a little nitty-gritty. So on the bottom side, you can see all the different individual phenolics that we quantify. And then you can see, again, the methanol fraction gave us the highest concentration of different individual phenolics. And you can see water had some, and then the water exhausted ethanol fraction didn't have really any phenolics left. But you can also see, because the methanol and water, they have different polarity, and they were able to extract different phenolics out of the olipomus. And this is why you see that the blue is the lowest concentration, the red is the highest concentration, and you can see there are some differences between the different fractions. Okay, so here's the scale up. So we know we can't stay with our analytical scale. We're trying to be useful for the industry application after all. And so we scale it up to the best of our ability in the lab, right? If we had a pilot plan, we could do this we do have a pilot plan, but we couldn't do this study at a pilot plan. But we use about 11 kilos of olipomus to start. And then again, we use similar extraction systems, and I can show you the data here. So for the water extraction, we were able to get a lot of the phenolics out of the olipomus, and then the exhausted fraction had very little phenolics that's left. And then again, here is an individual phenols. So in the water fraction, you can see, so let's just say, let's look at hydroxyterosol. So the compound that's fourth from the left, it has the highest concentration. And then along with 4-HPA, both of these compounds are known to have very high antimicrobial and antioxidant properties. And this is why we think olipomus has a tremendous potential when it comes to these kind of applications. And you can also see that that's removed in the exhausted fraction. So to summarize what we have done, we scaled this up. You can imagine this could be scaled up in a pilot plant as well, or in an industrial, with very little investment. We didn't use specialized equipment, which is simply use water for the most part to extract. And we were able to get most of the phenolics out of there. And the extracted phenols, they were really rich in hydroxyterosol and 4-HPA. And I cannot emphasize how important these compounds are when it comes to antimicrobial and antioxidant properties. And it showed that it has a robust antimicrobial effect against E. coli and Listeria. And then I think we're going to, now you'll find out what happens after you have phenolics exhausted olipomus.
Thank you, Dr. Wang. Good morning, everyone. The team at Cal Poly has been exploring the production of biomethane from olive pomace. So as previously mentioned, olive pomace consists of the fiber-rich material remaining after the extraction of olive oil. And additionally, we have also considered olive pomace that has undergone further processing for polyphenol extraction, as Dr. Wang just outlined it. Next. Another variable that was introduced is the addition of enzyme during the process. So why did we choose enzymatic hydrolysis to treat the pomace? In order to make biomethane, we need soluble carbohydrate. And the olive pomace is made of insoluble fibers. So if we can convert these insoluble fibers into soluble carbohydrate, we could increase the production of biomethane. Enzymes are a powerful and beautiful tool to convert insoluble fiber into soluble carbohydrates. And because the olive pomace insoluble fibers are made of different types of fiber, mainly cellulose, hemicellulose, and pectin, different type of enzymes could be added alone or as a cocktail. Next. You may wonder why we decided to produce biomethane and not another biofuel. Methane is an effective fuel due to its renewable nature and minimal additional greenhouse gas emissions. It can be produced locally, reducing dependence on external fuel sources. As listed on the right side of the slide, other biofuels such as biodiesel and bioethanol had several disadvantages, which also explain why we decided to focus on the production of biomethane. Next. So here's a summary of the various samples we work with. If we follow the horizontal path, you can see that the process begins with phenolic extraction from olive pomace, which was performed by Dr. Wang's team. We are left with two fractions, the phenolics extracted olive pomace, abbreviated PE for phenolic extracted and olive pomace, OP, and a phenolic-rich liquid. The PEOP is then treated with enzymes to increase the soluble sugar. This can be done two ways. One is by adding a new source of water, which is represented by the arrow going up. However, we discovered during the process that the phenolics-rich liquid contains a lot of sugars, too, a soluble sugar already, which are lost in this fraction. So we added a step to remove the polyphenol by using a resin to concentrate the sugar into the liquid in order to recycle the source of water and soluble sugar. We added this fraction we named phenolic extracted olive liquid during the enzymatic hydrolysis of the phenolic extracted olive pomace to increase the total concentration of sugar for biomethane production. At the beginning of the figure, you can see that we also applied enzymes directly to the olive pomace with added water as a control. So let's look at some results. The two columns on the left present the data for pomace before and after extraction of the polyphenol, focusing on the fiber fraction in the red rectangle. Cellulose, hemicellulose, and lignin did not change much, but all increased during phenolic extractions. Next. In this study, we used 4 different types of enzymes to convert the insoluble fibers, but since our time is limited, I will only report on one type of enzymes, the cellulase. But you should know that the other 3 all exhibited the similar behavior. This figure represents what we obtained starting from olive pomace, to which just water was added. So all the polyphenol were still in the olive pomace. We tested several concentrations of enzymes that are shown in different color here against the control in red, which does not have any enzyme added. All samples show similar trends, which is an increase of reducing sugar amount as the enzymatic hydrolysis increased to 21 hours on the x-axis, but we observe a plateau at about 5 hours of hydrolysis. As expected, the more enzyme was added, which is represented by the purple line at the top, the higher the concentration of reducing sugar. Next. When we take a closer look at the statistical analysis of the data, we observe that several combinations of enzyme concentration and hydrolysis times gave similar reducing sugar concentration. These conditions are highlighted in gray. We consider the condition that gave us the highest reducing sugar in a minimum amount of time, because time is money, and with the lowest enzyme concentration. And for this enzyme, with cellulase, it was 18 hours at 1% of enzymes. Next. We apply the same process to the phenolic extracted olive pomace, to which the phenolic extracted olive liquid sample were added. Similar trend, all enzyme concentration showed an increase of residing sugar that start rapidly from 0 to 3 hours, and then there is a slowdown, and finally we reach a plateau. Next. This table summarizes the results for the different samples when using a cellulase to convert the insoluble fibers. So if you look at the two last columns, of the two first tables. You can observe that with enzyme, if we start with just olive pomace, to which we added water, which is in the second table, or if we use the phenol extracted olive pomace with the phenol extracted olive liquid, we ended up with similar concentration of reducing sugar of about 18 to 20 milligram per milliliter. Similar condition without enzymes led to a concentration of around 12 milligram per milliliter of reducing sugar. So we have significantly increased the content of reducing sugar with enzymes. The techno-economic analysis will determine if extracting the phenol before adding the enzymes for sugar conversion is justified, or even the use of enzymes is justified. In other words, if the increase of reducing sugar is enough. So to summarize this first part, we observed that all 4 enzymes tested showed similar trends, but the condition to reach the highest reducing sugar content was enzyme dependent. We also observed that removing the phenolics did not increase the reducing sugar content, and that adding back the water used for phenolic extraction was beneficial. So the next step was to determine, because each enzymes act differently on the fibers, if the combination of enzymes of what we also called a cocktail could improve the amount of reducing sugar. So using 4 different enzymes, multiple hydrolysis duration, and 4 concentration resulted in a substantial number of samples. Next. So to manage this complexity, we employed a tool known as a response surface methodology, RSM. This approach helps us identify optimal conditions and understand the overall interaction between these parameters. So in this table, we have the result obtained for the phenolic extracted olive pomace with the phenolic extracted olive oil with different type of enzyme at different concentration. So for example, in the first row, the enzyme cocktail consisted of half-half, so 1% of cellulase and 1% of pectinase, totaling 2% enzyme concentration. And all the numbers in red in the last column identify the reducing sugar content with no significant difference. According to our model, the projected highest reducing sugar content was 22.3 milligram per milliliter, achieved with a combination of cellulase and pectinase. Next. Now for the anaerobic digestion part, the type of soluble carbohydrate could impact how much biomethane we could produce. And therefore, we looked at the sugar profile of all the samples that were produced. And that is a table that is on this slide. Next. To illustrate what we looked at, here are the results for 2 samples, one with half cellulase and half pectinase, and one with only cellulase, the run 7 and the run 1. These 2 samples had the same reducing sugar contents, but the first one had a higher glucose concentration, which is a hexose sugar. This indicates that while they had the same reducing sugar content, they had different carbohydrate profile, and this can impact biomethane production. We used these 2 samples to see if the carbohydrate profile difference will impact the methane yield. So the samples were treated with sludge obtained from the San Luis Obispo water treatment facility, leading to the production of both methane and carbon dioxide. To isolate the methane, the carbon dioxide was absorbed into a solution, allowing only the methane to be detected by a valve that measures the total gas output. Next. We obtained the following figures that show the methane yield in the y-axis for different samples. The top and the lowest curves represent just control sample. The curves in the middle of the figure showed our sample, and we can observe that regardless of the samples, with or without enzymes, similar amount of biomethane was produced. Next. Similar observations were made when performed the biomethane production with sample with or without polyphenol. So the polyphenol didn't have an impact on biomethane production. Next. So we demonstrated that enzymatic hydrolysis can increase reducing sugar content in olive pomace, and the study supports the viability of olive pomace as a feedstock for second-generation biofuel production, offering substantial environmental and economic benefits. So now I would like to hand it over to Dr. Fang, who will discuss the production of biochar.
Thank you, Dr. Yong. So in my section, I will utilize the digestion sludge from Dr. Yong's lab and then convert them into biochar and see how the biochar performs. So before I start, I just want to ask a question to you guys. Do you know what is biochar made of? It is carbon, right? It's carbon. So the process that we make a biochar is essentially to remove all other elements, right? Like nitrogen, hydrogen, and phosphorus through the process we call the pyrolysis, which is a carbonization process. We're heating the feeding stock at a very high temperature without oxygen, so that the remaining part, that we can remove all the other elements and keep all the carbon left. If there's oxygen in the process, then everything will be burned out. Nothing will be left over, only except for those ash. So in our lab, we actually used a equipment called a tube furnace to make that happen. But in more practical, large-scale production, people use biochar generator, which essentially just burning charcoal, and because that burning process exhausts all the oxygen, so it creates oxygen scarce environment to promote the formation of biochar. So that's a more economically feasible approach to make a large-scale biochar. And based on the recent the pricing that we found online, the price of biochar really varies significantly. We see some very high-end biochar is 2,000, 3,000 pounds per dollars per ton, and some very low-end ones with just 300 to 500, even very low price range. So really depending on the quality of biochar. So, and then the yield of biochar conversion also varies a lot depending on the temperature and the feedstock. So typically the higher temperature we apply, the lower yield it will be. So when we apply 600 degrees C, the yield will be down to 20–30%. When we use 300 degrees C, the yield can go to up to 40-something%. So depending on the biochar that we need, we'll apply different temperature and end up with different yield. So at the end of the day, we have to all run through this, to see what is trade-off, the cost and benefit, right? So if 300 degrees C is sufficient to produce a good quality biochar, then we'll use the lower temperature to keep the yield higher. So in our study, we utilized all different sorts of biochar, olive pomace as the feedstock in our study. So we used two temperatures, 300, 600 degrees C. When we use the original olive pomace, the yield is between 30% to 46%, depending on the temperature. So 300 degrees C, slightly higher, 600 degrees C, slightly lower. And we also use the anaerobic digested olive pomace, which is sludge, for the biochar feedstock. And then the yield can be much higher because in the anaerobic digestion residual, the majority of the compound left over is lignin cellulose humic substance, which can be highly efficient when they convert to biochar product. So the highest one that we can get at 300 degrees C, the yield can reach to 65%, which is very high. And then now I'm going to show you a bunch of data to see how our biochar from olive pomace compared to the commercial biochar. So the commercial biochar here we use is a product you can get is pretty much high-end one made by the tree trimmings. So when we use that, the performance will be way much higher. So the first one that we compare is total phosphorus removal. So that is one of the so total phosphorus removal is one of the water treatment indicator. So when we use a commercial biochar, we can almost remove 70% of the phosphorus from wastewater. And then our biochar, depending on the temperature produced, typically 600 degrees C once, regardless of original biochar or the anaerobic digested biochar, they can reach about 60% of the total phosphorus removal. So that number is comparable to the commercial ones, but those 300 ones are slightly worse performing. And also we compared the total organic carbon removal. So on this specific indicator, our olive pomace derived biochar is way worse compared to those commercial biochar. So actually, all the biochar did not perform well. So even for the commercial biochar, it only removed 45% of the total organic carbon. But when it comes to the olive pomace derived biochar, the performance range from 10% to 20%. So it's not very good for all total organic carbon removal. And also we look at the chemical oxygen demand reduction, because this is one of the very important parameter in wastewater treatment. That's something that the water will be the wastewater treatment plant will charge the fee based on this number. So if we look at the commercial biochar, they can reduce almost 80% of the chemical oxygen demand. But for the olive pomace biochar, the highest one that we can get is 35%. So on this indicator, it's a little bit different. And also we compared the heavy metal removal. So we used lead in this specific case. So this chart is slightly different from previous chart. So we kind of use the leftover lead as the marker here. So with the one with no biochar is basically the original lead solution. So that has the highest concentration. And then the commercial one was able to remove about 50% of the lead from wastewater. And our olive pomace, some samples really well performing. For example, the 600 degrees C of the original olive pomace can remove technically is this statistically similar number of the lead from wastewater, about 40%, but the remaining samples were way less performing. So as a summary, we found that the olive pomace can be converted to biochar at fairly high yield, from 30% all the way to 60-something%, depending on the feedstock and the processing temperature. And in some wastewater treatment application, for example, total phosphorus removal and heavy metal removal, our biochar is well performing. But in terms of the total organic carbon removal and the chemical oxygen demand reduction, this biochar from olive pomace is not that good compared to the commercial ones. So with that, I will turn to Dr. Huang to talk about all the techno-economic side of this project.
Good morning. My name is Haibo Huang, and I am associate professor at Virginia Tech, and my expertise is bioprocessing engineering and engineering economics. So today I'm presenting the work done by myself and my postdoc, Dr. Xuanbo Liu, at Virginia Tech. So the main purpose of a techno-economic analysis is to answer the key question: is this designed process to upcycle olive pomace economically feasible at a commercial scale? And what are the main economic drivers to make it economically feasible? Or what are the main barriers to make it economically unprofitable and avoid to kind of put a barrier over there to the commercialization? Next. Oh yeah, previous slide. So considering that a lot of the olive farmers and processors in California are small and medium-sized scale, we consider two processing models to process olive pomace. The first model is the centralized processing, in which farmers truck their olive pomace to a centralized processing plant for upcycling. And this business model can gain the advantage of economy of scale, potentially decreasing the operating cost. However, the capital cost for this centralized processing plant can be high. And the second business model is a decentralized processing. In this model, we design a small-scale mobile trailer to process olive palms in each olive farm sequentially. And this business model has a lower capital investment at the front end and is more flexible for individual olive farmer or processor. However, it usually meets economic challenges due to the lack of the economy of scale. So in today's presentation, due to the time constraints, I will mainly talk about the economic feasibility of the centralized processing model. Next. So this is a simplified process flow diagram of the integrated processing of olive palms to produce multiple value-added products, including biochar, biomethane, and polyphenol powder. So briefly, in this process, olive palms is first ground into powders, which is then mixed with water for the polyphenol compound extraction. And the extracted polyphenol is purified with resin, washed and spray dried to obtain the polyphenol powder. And after the polyphenol extraction, the solid residues is converted into biomethane through anaerobic digestion and the biochar through the pyrolysis process, as my collaborators talked in details before. Next. So the economic analysis are really based on the key processing parameters and the values collected by our experimental team, which represents the current state of art of the technology to upcycle olive palms. So you will see all those key values those are the authentic data from the anaerobic digestion group, from the biochar production group, or from the polyphenol extraction group. Next. So in this economic analysis, we assume that a centralized processing plant is located in California, close to olive producers and processors, and the project lifetime is 30 years, and we assume it takes about 1 year to build the plant, test and adjust equipment before full operation. And because olive harvesting and processing has a very short window, roughly two to 3 months, this creates a challenge for olive palms processing because it is economically challenging to build an expensive plant which can only operate 2 to 3 months per year and with the rest of 10 months stay idle. So in order to better utilize those expensive plant facilities, we propose to collect sufficient wet palms during the 2 to 3 months of the olive harvesting and processing window, dry these wet palms to 10% moisture to make it shelf stable, as Dr. Selena Wang showed, also dry powders of the olive palms. Then process these shelf stable palms throughout the whole year. Next. So with this processing design ready and experimental data fed by our collaborators, so we simulate the whole process with a throughput about 500 kilograms of wet olive palms per hour using the SuperPro designer. And this simulation helps us to determine the energy and the mass balance of the whole process, size and the number of the processing equipment like grinders, extractors, evaporators, as well as mass flow information between this equipment. And all this information are critical to determine the capital investment, operating cost, and finally the economic feasibility of this integrated process to convert olive palms into multiple value-added products. Next. So here's a complete list of the required equipment for the processing of the olive palms, including all necessary equipment used for olive palms pre-processing, like receiving and grinding, polyphenol extraction, and anaerobic digestion to produce biomethane, pyrolysis to produce biochar, as well as polyphenol purification and drying to produce powders. So due to the large scale centralized processing, the total equipment cost is about $970,000, which is pretty high. So besides the equipment cost, we also needed other direct and indirect costs to build the processing plant, such as equipment installations and adjustment, piping, engineering and supervision, as well as working capitals. So with all these expenses added together, the total capital investment for this olive palm upcycling plant is close to $2 million, which is pretty high for individual farmers. So and we would see that the majority of this capital cost is still the equipment purchase cost. So again, so centralized processing of olive palms, it gains economy of scales, but it didn't need a large investment of the capital at the front end. So after we estimate the capital investment cost, so we needed to estimate the annual operating cost to operate the plant, to convert the palms into the value-added products. And these annual operating costs included the raw materials, utilities, labors, and the property tax and insurance. The total annual operating cost is about $520,000 US, and among all the operating costs, the labor and supervision costs and the plant overhead accounts most of the total cost and almost account for half of the total operating cost. So these are the two biggest investment on the capital when we consider to open this business to upcycle the olive palms. And the next important part is our revenue. So how does our revenue look like? So there, as we mentioned, there are three major products from this olive palm through this integrated processing, which are biomethane from anaerobic digestion, biochar from pyrolysis, and the polyphenol powders from the water extraction of the olive palms. So we found that the most revenue are actually from the polyphenol powders, because polyphenol has a much higher market value compared with the biochar and the biomethane. The high-end polyphenol powder could be as high as $50 to $100 per kilogram, used as a food ingredients or some nutraceuticals. And whereas a biochar and a biomethane has a relatively market value per unit. And we look at one key economic indicator to show the economic feasibility or competitiveness of this olive palms upcycling, which is net present value. So usually when the net present value NPV value is larger than 0, it means it is a value-added process and the project could be economically feasible. So promisingly, we found that the net present value of this integrated process to upcycle olive palms is $0.85 million with a project payback time of 6.5 years. So indicating that this integrated process of olive palms can be profitable and it is a value-added process. That means, and the payback time of 6.5 years, that means like if you invest $2 million to upcycle olive palms, it takes about 6 to 7 years to get this money back. Next. So the sensitivity analysis tell us which parameters are most significantly affecting the economic performance of olive palms. And we found that the polyphenols market selling price, polyphenol extraction efficiency, and the polyphenol content in the olive palms could predominantly affect the net present value of the project, in other words, economic performance of this project. So this is not surprising at all because polyphenol carries the most value among these three products. And as a result of sensitivity analysis indicators that it might be a good idea for us to put more efforts on the polyphenol extraction and ensure its quality to enhance the economics of the olive palms process. So here are some take-home messages. Olive palms can be promising feedstock for producing value-added products with strong economic potential. And most of revenue of the olive palmate processing is derived from the extraction and the commercialization of the polyphenols, and the co-production of biochar and biogas can further enhance the economic feasibility of olive palmate processing. So this is the whole project summary, including all 4 objectives. So overall, we successfully developed and approved the concept of the integrated processing of olive palmate into multiple value-added products to support the circular bioeconomy of the society. And we have proved that we could scale up the polyphenol extraction process to extract phenolic compounds or in other polyphenols from olive palmate. And we also proved that olive palmate can be a good feedstock for methane production and also for biochar production. And more importantly, we showed that this olive palmate upcycling can be economically feasible with a strong market potential. So with that, thank you so much for your listening, and our whole team would happy to answer any questions you may have.
So you can unmute yourself, I think, and ask any of us any questions. We will also take volunteers who would like to start a mobile olive palmate processing truck. Also, this presentation is recorded, so you will be able to rewatch it if you like.
Yeah, so let me. Okay, Olga, you can talk now.
Thank you very much, everyone, for your presentations and your prior work. I have an olive mill, two-phase extraction, which means wet pomace coming out and oil. So wet pomace goes through the feed separation centrifuge. So I end up with this sludge or slurry, which is 82% of water. And the question is, so with that watery paste, what would you see, what would be next steps to come to final products? And what to do with wastewater in this case?
Yeah, so thank you, Olga. In another study, which we did about 10 years ago, that was also funded by CDFA, we actually look at the olive wastewaters, basically. So instead of the solids, we just look at the water. And what we did was to use a sequential membrane filtration to filter out the phenolics from the water. So that's one approach. If it's mostly dealing with a high water byproduct stream, you could also do what we did here. That would also work. But when we were dealing with our wet palmas, it was quite wet as well. So there's definitely some filtering that's needed, partially just to remove the high fermentation rate. And then because when fermentation happens, then the phenolics start breaking down. Ironically, when the fermentation happens, you actually increase the concentration of hydroxytyrosol, because the larger phenolics start breaking down to smaller phenolic, which is one of them is hydroxytyrosol. So that, if the goal is to maximize hydroxytyrosol, which is one of the potent and valuable compounds in olive palmas, that may be okay. So there are multiple approaches, and I think it's really depending on what makes sense for an individual processor.
Okay, so with water, I understood what's happening, but what was wet pomace in this case? And meanwhile, we're using olive peat for burning in a pellet stove to heating our facility. But the rest, with pomace, I'm trying to figure out how to make it bioavailable. And I also didn't understand what you name biochar. Like what the term? It's after you dehydrate, it's fully dehydrated powder, or it's some sort of fermented, still moist product. Yeah, if anyone could elaborate on it.
So yeah, so Olga, maybe I will try to answer this question, and maybe my colleague can jump in. So in your case, I believe that so you are trying to dry it, right? And then I think after drying, the olive pomace you can probably extract the polyphenol, and then the remaining portion, even without that anaerobic digestion, can be, since it's dried already, can be fed directly into the biochar generator to make biochar. And then adding that anaerobic digestion based on Dr. Huang's economic model probably is not going to affect significantly the economic performance. And even the biochar is only contributing 12 to 13%. So majority of the revenue comes from that polyphenol. So yeah, I think the first step probably is most important to me.
Okay. If I may ask another question related to the entire presentation. So we received the final byproduct, which is polyphenols. I guess they're in liquid form. Then biochar. So what about shelf life, those final products, and the way of storing them, and be able to, to use it further as a stream of revenue?
So I can answer the for the phenolics. So basically, after we have the liquid, we can freeze dry it to powder, or so then you can just store it in a freezer, basically a large freezer, and that would be stable for as long as possible. Basically, that's how we store all the phenolics in the lab anyway. So that's essentially, you reduce the volume and extend the stability of these phenolics by quite a long time. And I think the typical shelf life of like antioxidant supplements are like a year or a year and a half. So it will be similar to that.
But what about biochar?
For biochar, Olga, I think biochar is quite chemically stable, and as long as you keep it dry, it should last for years.
Yeah. So did I understand correctly? Biochar is used in agriculture as amendment, and also you can use it as a fuel. Is it correct understanding?
Olga, we don't use it as fuel, but we use it for especially soil and water. Yes.
Okay.
Yeah, if I may add, so biochar has lots of applications, though it depends on the quality of a biochar. From the low end, about $500, $600 per ton, you can, or to the high end, $2,000 or $3,000 per ton. So lots of biochars are currently used as a soil improvement, and also some of biochars are used to filter water, agricultural water or drinking water, and quite a lot of fraction of the biochar actually used as an animal bedding, like when one of our collaborators are using biochar in their chicken house to absorb those off flavors from the chicken house and to absorb those liquid from absorb liquid to keep it in a good environment.
Mm-hmm. Okay. Seems like it's a lot of further conversation need to be done. And industry meetings.
Yeah.
Yeah.
Thank you.
Okay. Thank you for your responses.
Thank you. And we have another question from the Patrick Smith. He's asking, what are the cost breakdown for mobile processing unit and the project break-even point? So Dr. Huang, do you want to address this question?
Yeah, so we designed this mobile processing unit and trying to put all those key equipment together into one mobile truck, and we assume that this mobile truck goes to process olive palms from one farm to another farm. And at this current point, we found that our current design of the mobile processing unit is not economically feasible, mainly because there are two things behind it. One is economy of scales, because when we design a centralized processing plant, so the large amount of the olive palm share the same amount of equipment, so that the best utilize the equipment, lower the production cost. And the second is that with a mobile truck, it could only run 2 to 3 months per year, mainly because that's only harvesting and processing time of olive product and producing olive palms. So at this point, our current design is not quite economically feasible, but we are still working on to see if we could simplify the process to make it profitable at one point.
Great. I think we're at time. So we want to thank all of you for coming today to listen to our work. That's really the last 3 years we've been working hard on this. So again, the presentation will be available and shared, and there will also be upcoming papers that cover what we presented today in more details. And thank you to all of my colleagues. This has been a really fun project to work together.
Thank you.